Hello. So today I want to discuss about a problem that appeared in INMO 2012. It's a functional equation problem, mainly a bit of polynomial-like functional equation, where sequence of functions are involved. So you will get a general idea to how to solve functional equations where sequence of functions are involved. At the end of this video, I'll give a similar type of polynomial functional equation where sequence of polynomials are involved. You will try that on your own, and once you have done it, you can type the solution in the comment box.
This video is sponsored by Chinta.com. Since 2010, Chinta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI-CMI entrances, and research projects for school and college students.
So let's begin. We define a sequence of functions by f naught x is 1, f1 of x is x, fn x whole square minus 1 is fn plus 1x into fn minus 1x. For n greater than equal to 1, I have to prove that each fn x is a polynomial with integer coefficients. So let's begin. Let's try to find out what is f2x, because I need to reduce this thing to a bit more, because only this thing won't be able to help us much. So I need to reduce it by putting n equal to n plus 1 or n minus 1. In either cases, f2 should be a bit helpful. So try to find out f2. So n equal to 1 gives me what? f1x whole square equal to 1 plus f2x into f naught x. So x square equal to 1 plus f2x, so f2x is x square minus 1. I have f2x equal to x square minus 1. Now in the main recursion, let's put n minus 1 instead of. So I replace n by n minus 1 to get fn minus 1x whole square minus 1. Okay, first write the first one. Fnx whole square minus 1 was fn minus 1 into fn plus 1x. I replace n by n minus 1 to get that fn minus 1x whole square minus 1 equal to fn minus 2x into fnx. What I can do to subtract that to get rid of that 1. So from that I get that fnx whole square minus fn minus x whole square equal to fn minus 1 into fn plus 1 times x. I'm just reducing 1x here, like whatever, minus fn minus 2 times x into fnx. Let's try to get the parts of fnx and fn minus 1x together. So what do we get? Fnx, take it common, we have fnx, and take this part to the LHS. So fnx plus fn plus 2x plus fn minus 2x. This should be equal to what? This should be equal to, I can take fn minus 1x common. This should be fn minus 1x plus fn plus 1x. So I can take things in denominator to get that fnx plus fn minus 2x by fn minus 1x equal to fn minus 1x plus fn plus 1x by fnx. Can I get something useful out of it? Let's think. If I call this function to be gn of x, what can you say about gn of x? Call this to be gnx, whatever. What can you say about gn of x? What if I put n by n minus 1? What do we get? We just get that gnx is same as gn minus 1x. So gn is just a constant on n. This is a very useful thing. This is really important. So I can iterate over again to get the gn. We can easily find what is gn is, because gn is a constant over n. Like gn is a constant polynomial. If I just vary n over, it doesn't matter. So what do we get? Gnx equal to gn minus 1. Then I equate it again to get gn minus 2, gn minus 3, and so on. So gnx is same as, okay, for what values of n gn is defined, because gn involves fn minus 1 and fn minus 1 is defined for n greater than or equal to 1. So gn is defined for n greater than equal to 1, so I can reduce it up to g1x. So this is same as g1x for all x in R. Now what is g on x? G on x is just f naught x plus f2x by f1x. F naught x plus f2x by f1x. F2x is my x square minus 1. F naught x is 1. 1 plus x square minus 1 by x. That is just x. So I get that gnx is x for all x in R. So gn is just the identity polynomial for all n. I also had what to be gn. So from that I get that fn minus 1x plus fn plus 1x. Fn minus 1x plus fn plus 1x by fnx, that was my gnx, so that is x. So by fnx equal to x. This is x times fnx for all x. So I get another functional equation that gives me fn plus 1x equal to x times fnx minus fn minus 1x. Now this is a very standard equation. You can easily guess that f should be a polynomial from here, just by induction. You already know that f naught, f1 and f2 are polynomials, and by induction you can easily say that fn plus 1 is fn is a polynomial for all n and integer coefficients. You can just use strong induction that fn minus 1 if fn minus 1 is a polynomial, then fn is also polynomial, and assume strong induction that fn minus 1 and fn are strong polynomials. Then in that case x times fnx is also polynomial, and sum and product of polynomials are polynomials. So fn plus 1x, that would imply fn plus 1x is also polynomial by induction. And you already just adding them and multiplying by x, and that doesn't change nature of coefficients, and coefficients being integer is preserved. It is also an integer polynomial, and you are done by induction. So you're done with this problem. Now I'll try you to do one thing on your own. Can you find the exact expression of fnx from here? Like fnx. What is the degree of fnx? What is degree of fn? And it is some a naught plus a1 times x plus a2 times x square plus up to dot dot dot. Can you find these expressions? Like, can you find the explicit expression for fn? Can you find this? Try that on your own. And I'll give an another problem. The problem is, define a sequence of polynomials Pn by P1 x equal to x, Pn plus 1x equal to Pnx whole square plus 1 for all n greater than equal to. Proof that a polynomial p of x satisfies the functional equation p of x square plus 1 equal to p of x whole square plus 1 if and only if it belongs to this sequence. So for that you have to show that the sequence of polynomials that is defined as above, we have to show that any polynomial from the sequence satisfies this equation, that p of x square plus 1 equal to p of x whole square plus 1, and conversely, if any polynomial satisfies this equation, it must lie in that polynomial sequence. Try this on your own, and if you find out the solution, you can type that in the comment box. And if you find functional equations and polynomial equations interesting, you can follow this channel. There are a lot of interesting stuffs here. Thank you.
Chinta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Chinta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Chinta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit chinta.com.